Hello everybody. Today I will discuss improved decoding of expander codes. So this is Chen from University of Science and Technology of China, based on joint work with Kuan Chen from Peking University, Li from Johns Hopkins University, and Minghui Ouyang from Peking University. Let us review some basic facts about coding theory. So given a binary code of length n with code words C1 till C1, C2, and so on, we define its distance to be the minimum Hamming distance among all pairs in C, and its rate to be log the size of C over the length n. Okay, so one factor that will be extensively used in this talk is that given the distance, say delta, the unique decoding radius of this code up to the distance delta over 2 for adversarial errors. Okay. So we will consider expander codes in this talk. So let me first define an expander. So expander has two parameters: the size of the subset alpha n and the expansion 1 minus epsilon d. Okay, so we call a bipartite graph with n vertices on the left and m vertices on the right, where it is d regular on the left hand side is alpha n 1 minus epsilon d expander only if for any subset S of size at most alpha n on the left hand side, its neighbor set called gamma S is of size at least the size of S times the expansion parameter 1 minus epsilon d. Okay. So the two parameters of the expander, the first one, alpha n, controls the size of the subset S. The second one, expansion, lower bounds the size of its neighbor set in proportion to the size of S. Okay. So one comment is that there's a trivial upper bound on the neighbor set that's d times the size of S, because the graph is d regular on the right hand side. So expander means that every subset of size less than alpha n has a highly non-trivial lower bound compared to this trivial upper bound d times S. Okay. So a few more remarks about the parameters. So usually we think n is a constant less than 1 times n. Say m is half of n in this talk, and alpha is also a constant. Okay. So then for the parameter epsilon in the expansion, so epsilon is at most half in this talk, and some results require epsilon to be less than 1. Okay. So then the degree d on the left hand side will be a constant, depends on alpha and epsilon. Okay. So, and we know explicit constructions with such parameters exist from previous work by Alone, Capabro, and Ringgold, Valham, Victorson. Okay. So that's all I want to say about expanders. So next, let me define expander codes, which are well known for the ultra efficient decoding algorithms. Okay. So given an expander with n vertices on the left and m vertices on the right, we define its expander code by assigning one variable yi to each vertex on the left and consider each vertex on the right as a parity check on its neighbors. So for example, the second vertex on the right will be a parity check on y1 and y4. Okay. So then the expander code associate or corresponding to this expander is all binary strings of plus n satisfies all parity checks. Okay. So one observation here is that the rate of this code is at least n minus n dividing n. Okay. So one more comment is that expander codes are closely related to LDPC codes. So while LDPC codes require the bipartite graph to be bounded or regular on the right-hand side, one can show that a random LDPC code will be an expander code with very good parameters, with very high probability. Okay, so that's the definition of expander code. So now let me tell you some previous results. The seminal work by Sipser-Spielman shows a linear time decoding algorithm called belief-propagation for expander codes. Okay. So specifically, given the parameter epsilon less than 1/4, the algorithm can decode 1 minus 2 epsilon times alpha n errors for any expander code where the parameters of the expander is alpha n and 1 minus epsilon times d. Okay. So the first comment is that this algorithm shows that expander code is a asymptotically good code with linear time decoding algorithms. So in fact, to the best of my knowledge, all known asymptotically good codes with linear time decoding algorithms are variants of expander codes. Okay, so that's one reason we are particularly interested in expander code. So the second thing is that it is folklore that the distance of the expander code is at least 2 times 1 minus epsilon times alpha. So you can see there is a gap like epsilon between the decoding radius of Sipser and Spielman and the half of this folklore distance bound. Okay, so then there are some previous works by Feldman, Malkin, Saverdio, Stein, Wainwright, and Madman separately that provide decoding algorithms with a better radius 1 minus 3 epsilon over 1 minus 2 epsilon times alpha. Okay. However, you can see a gap between this new radius and the half of the folklore distance. Okay. So while we are interested in improving the decoding radius, the first motivating question that we want to figure out in this work is that what is the best distance bound we can get from an arbitrary expander? So now I can tell you our main results. Our first result shows a better bound for any expander code. Okay, so basically, given any epsilon less than half, the distance of any expander with parameters alpha n 1 minus epsilon d will have its code with distance at least alpha n over 2 epsilon minus a constant. Okay. Okay. The first comment is that this distance alpha n over 2 epsilon is always better than folklore bound 2 times 1 minus epsilon alpha n for any epsilon less than half by a Taylor expansion. Okay. So in fact, this is much larger than the folklore bound where epsilon is tiny, say greater than the folklore bound by a factor of order 1 minus epsilon. We also show this is tight that the existing expander whose code has distance alpha n over 2 epsilon plus little. That's all I want to say about the first theorem. But then, given the new bound on the distance of the expander code, the next question will be, can we design ultra-efficient algorithms that decode more errors? In particular, if epsilon is small, can we decode like errors in the order of alpha n over epsilon instead of some constant times alpha? Okay, so we give a firm answer for this question. So we design a linear time algorithm that, given alpha and epsilon less than 1/4, it decodes 3 alpha over 16 epsilon times n errors for any expander code. Okay. The first comment is that this error is in the order of alpha over epsilon times n, which is better than the previous decoding radius by a factor in the order of 1 over epsilon if epsilon is small. But even when epsilon is large, say close to 1/4, this is still a constant factor better than the previous result. So it will. So when epsilon is close to 1/4, our decoding radius is basically 3/4 times alpha n. All previous results can only decode up to half times alpha n errors. But on the other hand, this falls slightly shorter of decoding half of the distance that we show in the previous slide. So that's 1/4 times alpha over epsilon. Okay. The last thing I want to say about our main results is that both theorems will use this new ingredient called size and expansion tradeoff. So this lemma will say that any expander with parameter alpha n 1 minus epsilon b expansion is also an expander for larger subset, but with worse expansion. Okay, so specifically for any k greater than 1, the expansion of subset with size k times alpha n is 1 minus k epsilon times d. That's all I want to say about our results. So the rest of the talk, I will first go over the technical section. I will sketch the proofs for theorem 2, assuming size expansion trade-off, and sketch the proof for level 1 about the size expansion trade-off. Then I will tell you some ideas behind our new decoding algorithm. And finally, I will give a summary and tell you some overview. Just for convenience in the rest of the talk, we will only consider expanders whose expansion is at least 3/4 times d. In other words, epsilon is less than 1/4. Okay. So let me first sketch the proof of theorem 2. So the basic idea is to combine the classic notion called the unique neighbors with our new ingredient, the size and expansion trade-off. Okay. So first, let me define unique neighbors. So given a subset S, we say a vertex on the right is a unique neighbor of S only if this vertex has exactly one edge connected to S. Okay. So the first vertex is not a unique neighbor. The second one, it is. The third one is not a unique neighbor, neither the fourth one nor the fifth one. Okay. So now let me show you the proof sketch. So the basic fact we will use that. So if there exists a unique neighbor in the neighbor set of the support of a binary string y, then y is definitely not an odd word, because the parity check of corresponding to this unique neighbor will only have exactly one from y. Okay. At the same time, because the expanded code is linear, if we want to bound the distance of this code, we only need to consider the support size of any non-zeroing binary string in this code. Okay. So in other words, I just want to know about the support size of y for any y to code. Okay. So let me first review the argument for the previous bound 2 minus 2 epsilon times alpha n. So the basic idea is that any subset S of size alpha n has at least 1 minus 2 epsilon times d times alpha n unique neighbors from the expression property. So then one can add at most 1 minus 2 epsilon times alpha n vertices to S, say S prime, such that there are at least one unique neighbor left, because each vertex in S prime can kill at most d unique neighbors. Okay, so because there's one unique neighbor left, S union with S prime is not the support of any code word, so we get a low bound. So our ID will be choose K to be 1 minus 2 epsilon minus little 1 in lemma 1, such that lemma 1 will guarantee that any T of size K alpha n has expansion at least half of D, more than half of D, because K is 1 minus 2 epsilon minus little 1. Okay, so this will imply that there is at least one unique neighbor of T. So that will imply that any y in C will have support size of at least K alpha. So this is the proof sketch of theorem 2. So you can see that the lemma 1 is crucial in this proof. So then let me tell you the proof of lemma 1 about the size expansion trade-off. So the basic idea is to apply a probabilistic argument about collisions. Okay. So, let me reformulate lemma 1. Lemma 1 is saying that given any expander with guarantee that any subset of size alpha n has expansion 1 minus epsilon times d. So we can show that any subset of size k times alpha n has expansion 1 minus k epsilon times d. Basically, we need to lower bound the size of the neighbor of the size of the neighbor set of any subset of size k times alpha n. So let's consider a fixed subset T of size k alpha n, okay, which is shown in the red color. So what we know is that any subset of size alpha n has the expansion 1 minus epsilon d. Okay, so we will show how to know the size of gamma t in this slide. So let me tell you how we define collision. So basically, a collision is a pair of edges from a fixed subset, could be S or T, that have the same right endpoint. Okay, so you can see for this vertex, it has two edges connected from S connected to it. So there's one collision. For this vertex, there are 3 edges connected to it. But we do not want to count it as 3 choose 2 collisions. We just want to count it as 2 collisions, such that the size of the neighbor set will be d times the size of itself minus the number of collisions. Okay, and we can define a proper order from all edges of this subset, say S, and then we, by the expansion guarantee we can show that the number of collisions of S is the most epsilon D times alpha. Okay. Now the basic idea is that if T, the largest subset or the superset of T, the superset of S, has too many collisions, then a random subset will have lots of collisions, which gives a contradiction to the above fact. Okay, so the basic calculation will show that if we look at a random S in T of size alpha n, the number of collisions is at least the number of collisions of T divided by K squared, because S is a subset of basically 1 over K times which 1 over K of T. Okay, so now I can plug the upper bound of the number of collisions of S on the left hand side. So this will help me upper bound the number of collisions of T, and that will give me the lower bound on the neighbors. That's basically the idea of this size and the expansion trade-off. Actually, we have better trade-off for larger K, say K greater than 1 over 2 epsilon, but I will not have time to discuss it here. So finally, let me tell you some our ideas behind the new decoding algorithm. The key observation is that we can improve belief propagation by guessing the expression of the error. So let me review the parallel algorithm of belief propagation. Okay, so it's very simple. So while the string Y is not a code word, we will flip all bits yi with 1 minus 2 epsilon d 1 checks in its neighbor. Okay, and I will do this flipping in parallel. Okay, so this is the classic belief propagation algorithm. So our key idea is that if we can guess the expression of y at every moment, say at this moment, the neighbor set of the support set of y is of size 1 minus gamma times d times the size of the support of y. For some gamma less than 2 epsilon over 3, then if we reset the threshold of 1 parity checks in belief propagation to 1 minus 3 gamma d instead of 1 minus 2 epsilon d, it does decode more errors. Okay. Then you may ask, what if gamma is larger than 2 epsilon over 3? So in the other case, we will apply another algorithm that finds the error positions in Y. Okay. So the final algorithm will be a combination of belief propagation and Weidman with this new idea of guessing expressions. So that's what I want to say about our algorithm. Let me summarize what we did here. So our main results are that the distance of expanded code is at least alpha n over 2 epsilon, which is tight if we only have the expansion guarantee. So then we provide ultra efficient decoding algorithms with radius 3 alpha over 16 epsilon. But just for epsilon less than 1. And we also have a new ingredient called size expansion trade-off, which may be of independent interest. So in fact, we have more results, but I do not have time to discuss. For smaller epsilon, we have more algorithms that decode a little more errors. And we also show the least decoding radius could be larger than standard Johnson bound for distance alpha n over 2. Okay, that's what I want to say about our results. So some open questions. One is the decoding algorithms for epsilon greater than 1 quarter. So as mentioned earlier, we have this bound 1 minus 3 epsilon over 1 minus 2 epsilon times alpha n from previous work. It actually holds for epsilon up to 1/3. And for epsilon close to half, Weidman's give an algorithm that can decode sublinear errors. Okay, that's n to the omega 1. So one can ask for n greater than half, but so sorry for n less than half, but greater than 1/4 can be decoded linear number of errors. Okay. So then the next question will be, can we design these decoding algorithms or for expander codes or for LDPC codes? Finally, the last question will be, can we show, is there any hard list result for decoding or list decoding? So that's all I want to say today. Thank you.